turning points today then. At a turning point for a function, we have generally, and we'll look at some shapes of these turning points in a second. So not always, but generally, these turning points tell us a maximum or minimum value for a function. So we're interested in them because we're interested in the maximum and minimum values. Differential calculus, we remember, gives us the gradient of a function, the rate of change at any point. And at a turning point, the gradient is 0. So let's have a look at some shapes of these things. Maximum value, okay, turning point. You can see the turning point here, and of course at that point the gradient is 0. Positive gradient here, negative gradient here. At some point the gradient changes from positive to negative, and at that turning point we've got a maximum value. Similarly, a minimum value, okay, the gradient starts off negative, drops to 0, goes positive again. If I differentiate a function, it's going to tell me when the gradient is 0. It won't differentiate between a maximum and a minimum value. Also, we have points like this can occur in functions. Luckily for us, not commonly, okay? And they're called points of inflection. So the function could come up like this with a positive gradient, drop to 0, but then carry on going up again. So it's not a maximum or a minimum value, it's called a point of inflection. And so we have to be aware that that might happen. So if you differentiate something, it's not necessarily giving you a positive, a maximum or a minima. And so we need to find a way of determining whether or not our 0 gradient is giving us a maximum value, a minimum value, or this point of inflection. Okay? Okay. So let's go through this through an example here, taken from the textbook somewhere. We're on turning point in the chapter on differential calculus, but don't worry about that. Here it is. We'll go through it together. Okay. We'll use this example to go through the steps that you go through to find a turning point. So the process is important here. Let's have a look at the question. Determine the turning points on the curve y equals 4 sine x minus 3 cos x in the range x equals 0 to 2 pi radians, and distinguish between them. In other words, are they maxima, are they minima, or are they points of inflection? Sketch the curve over one cycle. We'll not necessarily do this last bit. That's not quite so important. We're just after the maxima and minima values. If you want to sketch the curve, you type this into autograph. You're not going to go to the trouble of going through all this process. Okay? So let's just focus on finding these turning points and determining whether they're maxima or minima. So let's go through the steps. Step 1. Function y equals 4 sine x minus 3 cos x. We're after the turning point. The turning point's to do when the rate of change is 0, so what do you think we do first? Right, we differentiate it. The two variables here are y and x, so dy by dx. The rate of change of y with respect to x is 4 cos x, and cos becomes sine, but minus sine, because this is already negative, minus a minus becomes plus 3 sine x. So just beware signs when you've got those negatives in there like that. Okay? So that's step 1. We differentiate it. In this particular example, quite straightforward, but it could involve a function where we've got two variables, in which case you'd have to use the product rule or the quotient rule, something like that. Okay? We might need to use the laws of indices to simplify it, like we were looking at in the quiz. So differentiate it. Often that's straightforward. You just write down the answer, and there we are. So that's step one. We're interested in when this rate of change after the turning point. So what happens to the rate of change of the gradient at the turning point? Right, so we let the differential equal 0. That's step 2. Let dy by dx, the differential, equal 0. And solve for x. Well, I won't put for x because it's not necessarily x. So step 2, we let dy by dx equals 0 and solve. So 4 cos x plus 3 sin x equals 0. We've got to get x on its own. So what we do is we first of all take one of these functions over the other side, doesn't matter which one, but we'll take the 3 sin x over the other side, for example, so we can say 4 cos x equals minus 3 sin x. We're after getting x on its own. Now, we're after using, and this is what's going on in my mind, you get ones like these, there's a certain trigonometric ratio that I'm interested in now, and that's this. We're using this, that the tangent of x equals the sine of x over the cos of x. That's what's in my mind to use. So I'm going to get the sine function, divide that by the cosine function, so instead I can say tangent, okay? And then at some point I can find out what x is, because I can do inverse tan. Okay, so I'm going to divide both sides by cos x. So I've got sine x over cos x. Okay. So to be able to do this next step, I had to have that in mind, that was the trigonometric ratio that was going to help in this case. So 4 equals minus 3 over 4 tan x. Or let's put the intermediate step in, sine x over cos x. So that means that 4, what am I saying? I've taken the 3 over. Yeah, equals minus 3 tan x. I was thinking about the next step. So now divide both sides by minus 3. Minus 4 over 3 equals tan x. And now x is the inverse tan of negative 4 over 3. So therefore x equals the inverse tan of negative 4 over 3. And it's going to give me the answer in radians. So I get the calculator out and do it, checking my calculators in radians. So x turns out to be negative 0.93. At that point, you're going to get a maxima or minima, or one of these points of inflection. But because we're talking about sine and cosine waves, it's likely to be maximums and minimums, and generally it is. So let's look back at the question now, because of course we've got a sine. If we were to sketch this thing, then whatever it looks like, it's going to be some sort of wave like this. So there's going to be more than one point at which we've got maxima and minima. So in a case where we've got some periodic wave function, as in this case for example, we need to stipulate over which range of values we're going to be finding our value for x. And if you look back at the original question, it says find the determining points within the range x equals 0 to x equals 2 pi radians. In other words, within one cycle from 0 to 2 pi radians. So we've got that x equals the inverse tan of negative 4.3. And so if we plot this tangent function, then we get this. That's what the tangent function looks like, okay? And we're after negative 0.93, which is around about here. Negative 0.93. So that's negative 1. And this is 1 rather, this is negative 1. So negative 0.93 is going to be about here somewhere. Negative 0.93. Which corresponds to the value we had of minus 4/3 as the tangent. So in other words, instead of finding on the calculator what the inverse tan of negative 4/3, we could have looked at this curve, negative 4/3, negative 1⅓, gone to the function and looked for negative 1⅓, which would have been around about here somewhere. Negative 1⅓. In other words, the same place, okay? But we're after not this value, but the values between 0 and 2 pi. 2 pi radians, 2 times pi is about 6 point something. So here's 6. So we're probably after this value and this value. Okay? So we need to recognize that and then be able to work out what those points are on the cycle by seeing the periodicity. Okay? For this, okay? Yeah. Well, in radians, I want to stick to radians, Jordan. So pi there, this point here is pi. We are looking at this point, which is negative 0.93. So this point is negative 0.93. Right, so in other words, this point here must be pi take away 0.93, which is, somebody tell me what it is, please. So the first value we're interested, sorry, 2.21. And what about this one? What will this value be? 2 pi take away 0.93, yeah, which is, right. So those are our values that we're interested in radians, okay? If we wanted it in degrees, we could use a conversion factor. 180 degrees is pi radians and do the conversion. So those are the values we're interested in. At those points, we get a maximum or minimum values, okay? So that's step 2. Step 3. Identify the nature of the turning point. Is it a maximum value or is it a minimum value at these points for x that we've identified? Remember, we've got x equal to 2.21, 5.356. Have we got a maximum at that point at 2.21 or a minimum? Does the curve go, you know, is it a maximum value at that point or is it a negative value at that point? Is it a peak or a trough? So to do this, what we do is we differentiate. To do this, we find the differential, the second differential. Now, that's d2y in this case by dx squared. And that's how we'd say it, d2y by dx squared. The second differential. Third differential? Right. Okay, so we use these symbols. If we were using the notation f prime for the first differential, then we'd have f double prime for the second differential and f triple prime for the third, and so on. So those are the two notations for the second differential. No, no. So if we plot the curve, okay, Now what I'm plotting here is not the function but the differential. So I'm plotting the differential of the function on this axis against x. Okay? And what we're saying is that if we look at the maximum and minimums under here, just sketch them here, we can see that for a maximum value, the gradient is going from the negative side to the positive side for a minimum, isn't it? Okay, the gradient is going from negative to positive. And if I were to sketch this up here, I would find that as x increases, the gradient would start off negative and go positive. And so we'd have a positive value. So if I find a second differential, that's telling me the rate of change of the gradient. And if that's positive, so second differential is positive, then we get a minimum. Okay? Yeah. Hang on. So if we look at this, okay, the second differential is positive. So that indicates a smiley face, and so a positive value means that we've got, for the second differential, we've got a positive value, it means a minimum value. Other way round, if we're looking at a sad face, that means a maximum, okay? Because, again, the real reason this is happening, because as x is increasing, okay, then we're going from a positive gradient, so we're up here on this axis, through 0 at the maximum value, and then the gradient's going negative. So a plot of the differential against x would give us a negative gradient, and that would indicate a maximum value. Okay? If it's a point of inflection, it doesn't go. It stays one side or the other, so it doesn't work. So we have to come up with another way of finding that. If we put a value in, as we'll see, and the second differential turns out to be 0, then it's a point of inflection. Okay? So let's have a look at how this works for this. So for our example, the differential function, dy by dx, is 4 cos x plus 3 sin x. All we do when we find the second differential is differentiate again. So therefore, d2y by dx squared is, cos becomes minus sine, yep, so it's minus 4 sine x. Sine becomes cos plus 3 cos x. And now we put the values in. So let x equal the first value, which is 2.21, was it? So d2y by dx squared, remember we're only interested in whether it's positive or negative, because that indicates, a positive value indicates a minimum, because it's a smiley face. If we get a negative value, that indicates a maximum. Okay? So what we're going to do is calculate the value for this. We put it into our calculator, and we let x equals 2.21. So minus 4 sine 2.21, again making sure we're in radians, plus 3 cos 2.21 equals, right, so it's negative, therefore it's a maximum. One of the two, maximum. So putting in the values, x equals 2.21, x equals 5.356, we get that there's a maximum at 2.21 and a minimum at 5.356. Okay, a maximum value. The only thing we've got to do now is what? We know that there is a maximum value at 2.21. What do we do now? What might we be interested in? Not necessarily drawing it out. I've gone to all the trouble of finding out that there is a maximum when x equals 2.21. What would I then be interested in finding out? What is that maximum value? Okay, so step 4, the final step. So therefore, step 4, find the values of the maximum and minimum and how do you do that? Put it back in the yes. We do this by substituting the values for x into the original function. So maximum substituting 2.21 into the original function. For the minimum, substituting 5.356 for the original function. And that will tell us the magnitude of those turning points. And they are. And the values turn out to be 5 and -5. And if we sketch the function, we can see our confirmation. And if we put this on the autograph, then we'd have seen it. Okay, so at 2.21 there's a maximum value and the value is 5. At 5.356, whatever it was, there's a minimum value and that's -5. So in other words, we can find the turning points on this function using calculus. 4 steps. Step 1, differentiate. Step 2, let that differential equal 0. Step 3 sorry, and solve. Step 3, determine whether or not they're maximum or minima. And step 4, if you need to, put those values for x back into the original function to find the sizes of those maximum and minimum values. That's it.